Encyclopedia Galactica.
The sky at night, a mountaintop window on the cosmos, the view of infinity. And high above, space telescope, probing the depths of distance and time. Gathering images like this from the edge of the visible universe, a brilliant primordial jet streaming from a quasar. By comparison, a mere galaxy is minuscule, but better understood. A cloud-like collection of perhaps 100,000 million stars. Swirls and spirals. Galaxies have condensed over some 15 billion years into the celestial patterns we see today. Encyclopedia Galactica charts the cosmos, setting the abundance of scenes like this against the utter emptiness of the universe. Pictures and data gleaned from space probes and the most powerful instruments on Earth. And new theories, one on galactic evolution. Here a photograph of two galaxies in close encounter. Modelled on computer, they seem to unravel each other. It's clear in reverse how this cosmic kiss changes their shapes. Beyond, and galaxies appear as clusters, each point of light a group of galaxies. These vast strands encircling unimaginable voids are the structure of the universe. Our own galaxy, the Milky Way, is an unremarkable spiral. Old stars at the center, younger ones in the outer reaches. Within the galaxy, these are the stars themselves, each dot a sun in its own right, hundreds upon thousands upon millions. Closer to, and clouds of bright gas and dark dust as material billows from energetic new stars. Unlike the Sun, most stars are pairs or triplets. These three are the system Alpha Centauri. After the Sun, they are Earth's nearest stellar neighbours. Even so, their starlight takes more than 4 years to reach us. At 45 light-years away, the 6 stars of Castor, 3 sets of twins, all in orbit. Encyclopedia Galactica attends the birth of a star, a swirling cloud of gas and dust falling in on itself. As it coalesces, so temperatures soar. They trigger nuclear reactions. A star is born. And a star dies, its final breath a great nebula, the corpse a tiny pulsing neutron star. This photo of the Gum Nebula is the remnant of such a catastrophe. But its debris can recycle to spawn new stars, like the Sun. Born 5 billion years ago, the Sun is just 8 light minutes from Earth. The local specimen of a rather ordinary type of star. X-ray reveals its nature. The sun is a nuclear furnace, a turbulent colossus where every second 4 million tons of hydrogen is turned into helium. Encyclopedia Galactica cruises the planets, a journey through the 9 worlds of the solar system. To the red planet, Mars. A ride down Mariner Valley, 20 times bigger than the Grand Canyon. The contours are exaggerated, but this is virtual reality, volcanoes and all. These are the features of Mars interpreted by computer. The source, photographs and data radioed by space probes. Onward and outward to Jupiter and its many moons. This is the giant of the solar system, 2/3 the mass of all the planets combined. Time-lapse of Jupiter, among the most exotic sequences in the history of space photography. The camera was aboard Voyager, one of 2 robot explorers which have unveiled the outer planets. They photographed Saturn. Twin probes whose parting tryst glimpsed the beguiling Saturnian rings. As Voyager 1 spun away into the galactic void, Voyager 2 set course for Uranus. It revealed a cool giant with an intriguing moon, Miranda. Close up, Miranda was a symphony of icy cliffs towering 20 kilometers or more. And around Uranus itself, Voyager detected a powerful magnetosphere. Four years later, and Voyager's final rendezvous, Neptune, another gas giant, and a place with the coldest surface in the solar system, Neptune's great satellite, Triton. And far beyond, Pluto with its moon, a mission yet to come. A flight over Venus. Of the inner planets, the Venusian surface has been the hardest to see, for it's enveloped by permanent cloud. Now, thanks to radar mappers, computers have visualized this, a ghostly topography, scuffed like an ocean bed. Venus, on the left, lies second nearest to the Sun. Tiny baked Mercury has the closest orbit of all. Planet by planet, Encyclopedia Galactica catalogues the pictures and the facts. It explores Earth as a planet. The collective satellite and computer data of NASA, the former Soviets, the Japanese, the Europeans. Above all, Encyclopedia Galactica places our beautiful, fragile world within the immensity of the universe. From the Big Bang, the formation of the galaxies, to the evolution of this planet Earth. And practical guides, learning the night sky, how to use telescopes and cameras, where to go, what to do. Plus the story of manned spaceflight, not just the past, but plans for a mission to Mars and a return to the Moon. To understand the nature of planet Earth, we must study the powerhouse at the center of the solar system, the body that heats and lights our world, on which everything, including humankind, depends. The Sun. The Sun is a star, an enormous nuclear reactor generating prodigious energy. Swirling magnetic fields, dark regions called sunspots, and searing eruptions of flares and prominences. Triggered possibly by the shock waves of an exploding star, the story of the Sun began some 5,000 million years ago, a whirling cloud of gas and dust that became increasingly concentrated. Within the cloud was all the material necessary to form the Sun and the planets. As the cloud condensed, so its central gravity increased, a vast aggregation collapsing on itself. The densest material at the center became intensely hot and nuclear reactions began. An embryonic sun had formed. Meanwhile, throughout the rest of the cloud, great swirls of material were shaping the 9 planets of the solar system. Today, the Sun is middle-aged, one of the 100,000 million stars in our galaxy, the Milky Way. Compared to Earth, it's gigantic. With a diameter of nearly 1,400,000 kilometers, the Sun is over 100 times wider than Earth, 1,000,000 times the mass. Even sunspots are several times bigger. The secrets of the Sun are revealed in its light, beams that can be caught and analyzed in solar observatories. Sunlight is a rainbow of color, a spectrum. Break it down and dark lines appear, fingerprints of the elements which make up the Sun. And they give us other clues to temperature, speed of rotation, magnetic activity. Here, the red fingerprint of hydrogen. This time-lapse, which filters only red light, reveals a Sun composed 3/4 of hydrogen, 1/4 of helium, and rotating in 27 days. Surface temperature, 6,000 degrees Celsius. In imaginary cross-section, the temperature at the core is 15 million degrees. Every second, nuclear fusion turns 4 million tons of hydrogen into helium. The energy produced takes eons to reach the surface. A total eclipse is another aid to solar study. It displays the tenuous outer atmosphere of the Sun, the corona. This is time-lapse of an eclipse from Java. The Moon, in orbit around Earth, is passing directly in front of the Sun. Only when the eclipse is total will the corona appear. As totality approaches, a strange twilight descends. Observers have trekked from many parts of the world to witness and record. And there's a diamond ring corona, just ahead of totality. The moon now covers the sun. An exposure change, and with it, the full magnificence of the corona. We're looking at a halo of hydrogen particles extending millions of kilometers into space. Totality was to last 5 minutes, 7 seconds. Precious moments, for the corona is so sparse that it's glimpsed only when the glare of the sun is obscured. Yet another way of looking at the sun is in soft X-ray. The small image is the same picture in visible light. They show the intense activity of sunspots. Sunspots are probably caused by powerful magnetic force lines. They're tangled and distorted by the sun's rotation and by its churning surface, the yellow photosphere. In close-up, the dark areas are sunspots. The bright regions, thousands of heat bubbles, each measuring 800 kilometers. This sunspot appears dark because it's 2,000 degrees cooler than the surrounding photosphere. The center is called the umbra, its edge the penumbra. A group of sunspots. They take up to 10 days to form and 2 weeks to fade. In quiet periods, there may be no spots at all. These sunspots were filmed in 2 different wavelengths. Here in visible light, now in the red light of hydrogen alpha. Both show huge arcs bent around magnetic force lines. The whale's fin is a prominence, the silhouette of a gigantic billow of gas. And there's another. Such plumes lick right through the sun's atmosphere, the red chromosphere. This one in black is set against the bubbling photosphere, the sea of firestorms at the solar surface. Prominences can extend 1,000,000 kilometers, this one suspended in a magnetic arc. But the most spectacular phenomena are flares, eruptions with the energy of 10 billion megaton bombs. Bottom left, shock waves radiate from an exploding flare. Remember, the sun is a gaseous mass. Flares eject stupendous quantities of material at millions of kilometers per hour, energized particles hurtling outwards as part of the solar wind. On Earth, they can disrupt telecommunications, but largely they're deflected by Earth's magnetosphere, except at the poles. There they create auroral rings as the particles are drawn earthwards. From beneath, the result is spectacular. The aurora, charged solar particles reacting with the atmosphere like a giant television tube. From the interstellar cloud that formed the solar system came not just the sun, but the 9 planets. As the heat of the sun increased, so lighter elements were driven outwards. They formed gas giants like Jupiter and Saturn. Heavier material nearer the sun condensed into the inner planets, including Earth itself. Our embryonic world whence sprang life and humankind. We are truly children of the stars. Orbiting closest to the Sun, Mercury, Venus, Earth and Mars, the four rocky midgets of the inner solar system. Bathed in warmth and sunlight, they're solid little planets with hard-baked crusts. The outer planets, except for Pluto, are giant spheres of gas, chilled in twilight. From Earth, by far the brightest planet is the rocky midget Venus. Over a season, Venus and Mercury skip through the sky close to the horizon. In fact, the view is of their tight solar orbits, best seen at dusk or dawn. Mercury on the right barely clears the skyline. Nearest the Sun, it's hardest to see. Venus takes 224 days to orbit the Sun. Tiny Mercury, just 88. At less than 70 million kilometers from the Sun, Mercury is perpetually scorched and irradiated. These pictures from the early 70s were radioed from the space probe Mariner 10. They reveal a surface pocked with craters, barren and still. Temperature by day, 460 Celsius. By night, minus 170. Gravity, 1/3 of Earth's, and no atmosphere. A cracked and battered little world. But why so many impact craters? The answer is the Sun. Its powerful gravity draws in debris from space. With Mercury in line of fire, it takes a lot of hits. Mercury's surface is like the hidden side of our moon. Both have great circular basins. Indeed, Mercury isn't much bigger than the moon. The planet Venus is altogether bigger. Almost Earth's twin in size and density, but completely veiled in swirling cloud. Not until a series of Soviet missions was the truth to be known. The object was to penetrate the Venusian fog and soft land on the surface. It was a descent into hell, atmosphere 90 times heavier than Earth, temperatures to melt lead, visibility just 3 kilometers. To this day, these are the only photographs of the surface. They were zipped to Earth before the lander cameras frazzled. The rock was basalt, probably fractured slabs of volcanic lava. Radar was to provide a better picture. Orbiting mappers electronically stripped the clouds to give the first wide-angle images of Venus, and volcanism was confirmed. But this was a flatter planet than expected. There were few craters and less contour than on Earth or Mercury. The impression was of an ocean bed, smoothed by the motion of currents. And radar had more delights. The globe without cloud, and in reverse rotation to all other planets. And radar let us fly. This is the topography of Venus, visualized on computer. Heights are exaggerated and color guessed at, but otherwise the features are accurate. The animation has been meticulously rendered from a global portrait compiled by Radar Mapper, a montage of thousands of radio snapshots through the clouds, like the echo soundings of a ship at sea. It works like this. As the mapper orbits, thousands of pulses a second are bounced to the surface. They sense details as small as 100 meters. In each 3-hour orbit, the mapper records a swathe of information 20 kilometers wide. In less than 250 days, most of the planet can be swept, the data ready for computer animators on Earth. Thus, in the 1990s, has the American craft Magellan been brilliantly at work. A Magellan image of volcanoes and fractures. A sinuous channel, possibly a lava flow. Fold mountains called Freya. A corona. Remember, these are radar images, not photographs. Cleopatra, a double ring crater. The Acna Range with an asteroid crater. Volcanic extrusions like mushrooms. Crater Golubkina, 34 kilometers across. And the Dickinson crater, first as a still, and now in animation, one of a trio, as we skim the Atlanta plain of the northern hemisphere. Most of the planet is rolling uplands. The two largest regions are like continents. Ishtar Terra, the size of Australia in the north, Aphrodite Terra, as big as Africa, to the south. Everywhere is evidence of volcanoes, but so far no sign of activity. Venus is the most volcanized planet in the solar system. Magellan discovered linear mountain belts, a feature shared only with Earth. But the scarcity of craters compared to Mercury or Earth's moon suggests a young landscape. It means also a surface shielded from bombardment. All but the biggest cosmic missiles would vaporize in the dense Venus atmosphere. This is like the bottom of the sea. These pancakes are volcanic eruptions squashed by atmospheric pressure. Such formations can be found in the depths of oceans on Earth. Magellan's imagery cannot convey the hell of Venus, a crushing, poisonous atmosphere of carbon dioxide, clouds of sulfuric acid, temperature 450 Celsius. This is the more likely scene, an inferno where light is bent and heat has no escape, the ultimate greenhouse effect, plus non-stop thunderclaps. Were this photography instead of radar animation, we'd see sulfuric acid clouds reacting with this volcanic peak. Venus is weird. It revolves so slowly that a day is longer than a year. And it's windy. In 4 days, the massive cloud blanket blows right round the planet. Venus resembles a little understood period on Earth, from the time shortly after Earth's crust had cooled to the emergence of life. Why Venus should have remained sterile and tormented is a mystery. The Galileo spacecraft, looping the Moon and Earth. An orbital slingshot to pick up speed for a mission to Jupiter. A detour with a bonus. En route, Galileo had captured the first pictures of Earth in rotation. The date, December 1990. The sun's reflection skims across the Pacific towards Australia. Our blue Earth, third planet from the sun, at a distance of 150 million kilometers, neither too hot nor too cold. The ideal incubator for life. These are satellite pictures, a compilation of thousands of cloudless images which show Earth as never before. Now we see the upper atmosphere, the aerosols of the ozone layer. Here in motion, it's this filter that protects us from solar radiation. During 2,000 million years, plants have changed our atmosphere by breathing oxygen into it. Today, CFC emissions may be changing things again, starting with this hole in the ozone at the South Pole. Earth has a busy atmosphere, 21% oxygen, 78% nitrogen. Without it, there'd be no life. And yet we threaten it by burning fossil fuels and forests. Each year we spew 7 billion tons of carbon dioxide into the air. We are gambling with immense natural forces. The energy in one day of a hurricane would power all industry in the United States for a year. We're at the mercy of our atmosphere. Weather satellites help us understand the atmosphere, the life-sustaining engine that maintains a mean global temperature of 15 degrees Celsius. The wind systems are driven by hot air rising at the equator. Their direction is modified by the spin of the Earth. Carbon dioxide keeps the planet warm by trapping heat. Scientists say we're producing too much carbon dioxide. They worry that it'll cause overheating, threatening a lifeless inferno like Venus. The rotation of Earth means that sunlight falls on only half the planet at any one time. From the surface, the sun appears to move from east to west across the sky. In fact, the sun is still. It's our planet that's moving, a 24-hour rotation causing day and night. This time-lapse through the night has the moon, top left, sinking in the west. And here, the Milky Way and the stars seem to travel through the heavens. Again, it's not the stars that are moving, it's Earth rotating on its axis. Were the axis upright, day and night would be the same the world over, but it's not. Earth is tilted 23.5 degrees from vertical. This varies the length of day and night. Add to that the complication of Earth orbiting the Sun, and there emerges an explanation of the 4 seasons. It takes Earth a year to orbit the Sun. Each day, the angle at which sunlight falls on Earth changes slightly. Over a season, it's quite a lot. In the 6 months from winter to summer, the change is greatest of all. From this position, it's summer in the northern hemisphere. The north has short nights and long days. The equator hardly changes. The south has long nights and short days. From this opposing position, it's winter in the northern hemisphere, short days and long nights in the north, long summer days and short nights in the south. From Earth, this means the midwinter sun is low in the sky. At midsummer on the same latitude, it's higher. This satellite sequence shows another seasonal change, the northerly advance of vegetation growth as the northern hemisphere tilts towards the sun. In Antarctica, the seasonal ebb and flow of the ice cap. Summer, and now the return of winter. Ten 10,000 years ago, the northern ice cap reached as far south as New York and London. It's uncertain, but such ice ages could be caused by a periodic wobble in Earth's orbit. Satellites monitor global temperature. Currently, we're enjoying an interglacial period. Temperatures are steady, although over the last 100 years, they've risen by 0.9 of a degree Celsius. "71% of Earth is ocean. The rest began as a supercontinent 250 million years ago. Ever since, its component parts have been drifting on plates towards the positions they occupy today. The red dots are volcanoes. They mark cracks where the plates meet, like pieces of a jigsaw. Even now, at a few centimeters a year, the drifting continues. Under the oceans, the plates are either pulling apart or pushing beneath one another. This lava lake is like plates parting, and this like plates subducting. Where plates interact, volcanoes erupt. This is the Mount St. Helens volcano, on the line between the Pacific and the North American plates. A visible reminder of Earth's volatile interior. From above the clouds, the plume of the Mount Pinatubo eruption in the Philippines. Stratospheric pollution that reduced Earth's temperature by 1 degree as volcanic ash girdled the globe. Before Pinatubo, a sunset with stars. Afterwards, a red atmospheric haze. These are the lights of Western Europe, another pollutant that obscures the stars. How clearly we'll see the cosmos in the future depends more on the human factor than occasional volcanic eruptions. These are the first pictures of the Moon and Earth moving together in space. They came from Galileo in December 1992. Slingshotting towards Jupiter, the probe had captured a new perspective, Earth with its only natural satellite, the Moon. These close-ups showed the lava fields of the Moon, differentiated in false colour. They were a chance to test Galileo's equipment, for in 1995 the craft will be imaging the moons of Jupiter. Meanwhile, Galileo was over the lunar North Pole, a region difficult to see from Earth. Like much of the surface, it's pocked with craters, the impacts of meteorites during 4.5 billion years. An ancient, barren terrain untouched by wind or weather. Although there's no air to breathe, the Moon is ripe for colonization. Next century, there's every possibility that permanent lunar bases will be under construction. They'll be like Antarctic research stations, but more self-sufficient. A network of pressurized modules to sustain human life. Oxygen may be produced from lunar rock, and water by chemically combining oxygen and hydrogen. Biospheric tanks will be the farms of the Moon. Augmented with organic fertilizer, food crops will grow in lunar soil, in lunar greenhouses. From these bases, pioneers will explore the Moon. They'll travel much further than their 20th century predecessors. The search will be on for industrial opportunities, like mining raw materials. And there'll be science, radio astronomy, free from the noise suffered by receivers on Earth, and photography, cosmic pictures without atmospheric distortion. This is the Moon from Earth. And these are scans through a telescope, like the view from an orbiting satellite. A huge crater, and mountain ranges reminiscent of the planet Mercury. The bright highlands, peppered with craters. The dark seas that cover 15% of the surface. In fact, they're impact basins filled with ancient lava. Flat expanses contrasting with the rugged uplands. And again, from over 400,000 kilometers away on Earth, the crater Copernicus. Our view of the Moon is constantly changing. If observed at the same time every night, the Moon shifts to the east, and its phases change from a crescent to a full moon and back again. One thing is constant. The Moon always presents the same face to Earth. That's because the Moon turns once on its axis in exactly the time it orbits once around Earth. So, whatever the phase, it's the same old face. How much of the face is in light depends on its angle to the sun. At new moon, we see nothing at all. The shadow is total. It's not Earth casting the shadow, but the moon itself in relation to the sun, a continuous monthly cycle. A view from over the poles has the moon and Earth catching sunlight from the right of the picture. As the moon orbits Earth, so it waxes and wanes to an observer on Earth. The cycle takes around 28 days. Here it is again, with the central frame showing the moon phase we see on Earth. Like the moon, many planetary satellites are trapped into showing the same face. Only if the moon's orbit stopped would its rotation be apparent on Earth. Compared to Earth, the moon is tiny. It would fit across North America. Earth's diameter is 4 times the moon's. Earth is some 12,700 kilometers wide. 30 Earths would reach the moon. Such proximity means the moon exerts a strong gravitational pull. Witness our ocean tides. The moon tugs on the oceans. A combination of its orbital movement and the rotation of Earth causes an ebb and flow that can make an island out of a promontory. This is an eclipse of the moon, caused as it passes through the shadow of Earth. On average, there's a moon eclipse once a year. With Earth starting to blot out light from the sun, the shadow on the moon appears red. The shadow is much bigger than the moon. Our dusty atmosphere bends the light of the sun to produce the red glow. While a total solar eclipse lasts minutes, a lunar eclipse can be hours. This one, in 1992, had a black shadow, clearly showing the curvature of our planet. The moon is 400 times nearer to Earth than the sun, an amazing coincidence, especially at a solar eclipse, when the moon's shadow scoots across Earth. Now, because the sun is 400 times the diameter, the moon can fit exactly over the disk of the sun, a total solar eclipse. Sometimes the moon isn't quite big enough. This is an annular eclipse. The reason is the moon's elliptical orbit, which periodically takes it slightly further from Earth. The moon is our nearest neighbour, the second brightest object in the sky. We know that moonshine is reflected sunshine, and that men have walked on the moon. But what's its origin? Is it the child of Mother Earth? Very possibly. For shortly after Earth had formed, it's believed to have been struck by another protoplanet. As it reformed, lighter material was blasted into orbit to become the moon. Gradually, it cooled. A lunar crust solidified. But over eons, the moon was bombarded by cosmic debris. Great basins were left. They filled with molten rock flowing from the interior. These hardened to shape the moonscape we know today.